Okay, so when we last left off, we discussed acids and bases. There's another subclass of compounds in terms of acid-base behavior, and these compounds are known as amphiprotic substances. Now, the key feature of an amphiprotic substance is that the substance can act as either an acid or a base. A substance, quite simply, an amphiprotic substance is a substance that can lose or accept a proton in acid-base reactions. So one of the more prolific amphiprotic substances is water. So water can function as an acid in some reactions. So for example, if we treat water with a strong base, such as, for example, sodium hydride, oops, liquid there. So if we treat water with a strong base such as sodium hydride, we end up generating hydroxide. So in this case, water is functioning as an acid, and it is donating a proton. If we take water and we treat it with a strong acid, such as hydrochloric acid, we can end up with water functioning as a base, whereas it is accepting a proton to generate hydronium ion. So, does everyone notice in this example that water can function as either an acid or a base depending on the conditions? This is called an amphiprotic substance. Does this idea make sense to everyone? Can I get some feedback in the chat that everyone's comfortable with this first premise? Okay, perfect. Now, the next major feature that we have to consider, is the fact that water undergoes auto-ionization. Water can actually react with itself. Because water is amphiprotic and it can act both as an acid and a base, it can undergo reaction with itself, and this reaction is known as an auto-ionization reaction. So one water molecule is acting as the acid, the other water molecule is acting as the base, and there's the transfer of a proton from one water molecule to another to make hydroxide and H3O+, or hydronium ion. Now, we can model and we can look at the concentration of ions, and we express this reversible reaction and the concentration of hydroxide and hydronium ions at equilibrium using the equilibrium constant. And K equilibrium looks at the concentration of products, anything with an aqueous symbol in the products, over the concentration of reactants. Again, anything with an aqueous symbol in the reactants. Since our starting materials, since our reactants are liquids, it just simplifies to the concentration of products with an aqueous symbol. Okay, so in this case, our two products are hydroxide and hydronium. So we can model the concentration of hydroxide and hydronium at equilibrium using the constant Kw. And Kw is defined as the ionization constant of water, and it has the units of 10 to the negative 14th molar squared at 25 degrees Celsius. So what this is saying is that if we look at the product of the concentration of hydroxide times the concentration of hydronium, if we're looking at a sample of pure water, this product will be 10 to the negative 14th molar. Now, we can take this one step further. If we look at for pure water, we see in this equation, The reaction produces an equal amount of hydroxide and hydronium ion. So the concentration of hydroxide and hydronium are equal. Thus, at 25 degrees Celsius, we can rewrite Kw into Kw, which is equal to 10 to the negative 14th molar squared, is equal to the concentration of hydronium times the concentration of hydronium. And in turn, we get the concentration of hydronium, which is equal to the concentration of hydroxide, is equal to 10 to the negative 14th to the 1/2. And that in turn gives us a concentration of hydroxide and hydronium for pure water at 25 degrees Celsius is 10 to the negative 7th molar. This is for pure water. Does that idea make sense to everyone? Does this concept make sense? So water auto-ionizes in solution, and we can model and we can calculate the amount of hydroxide and hydronium at equilibrium using Kw. So for pure water, we find that the concentration of hydroxide and hydronium are equal at equilibrium at 25 degrees Celsius for pure water, and their concentration at equilibrium is about 10 to the negative 7th molar. Does that idea make sense to everyone?
Professor, what's the answer that you have 1 to the negative 14? What is that at the bottom?
So this is 10 to the negative 14th.
Oh.
This comes from Kw.
Okay, 10 to the negative 14.
Yeah. So 10 to the negative 14th molar squared is Kw. And if we're solving this expression, this H3O plus times H3O plus gives H3O plus squared. And so to solve for the concentration of H3O plus, we're taking the square root of Kw, which is why we have 10 to the negative 14th molar squared to the 1/2. And that gives us the 10 to the negative 7th if you punch that into your calculator.
Okay, thank you.
So let's keep going now, and let's show how we can utilize this Kw expression to model the concentration of hydronium and hydroxide at equilibrium. So in the first question, we're asked, what is the concentration of H plus when the concentration of hydroxide is 2 times 10 to the negative 3rd molar? So we know that Kw is equal to the concentration of H3O plus times the concentration of hydroxide, and it can also be written as the concentration of H plus times the concentration of hydroxide, and Kw is 10 to the negative 14th molar squared. Okay, so with that in mind, we know what Kw is. We know the concentration of hydroxide. So solving the concentration of H3O plus, which equals the concentration of H plus, is just equal to Kw over the concentration of hydroxide. So we have 10 to the negative 14th molar squared over the concentration of hydroxide, which is 2 times 10 to the negative 3rd molar. Now, punching that into our calculator, we get 0.5 times 10 to the negative 11th, which corresponds to 5 times 10 to the negative 12th molar. Does that make sense to everyone? And then remember, when you're dealing with powers of 10, you enter this entire number on the bottom in parentheses into your calculator. Otherwise, you may end up not encapsulating the power of 10, and your number will be off by orders of magnitude. Does this make sense to everyone? Any questions on this example? Okay, so let's try now to work on the following example. So I'd like us to take about 3 minutes and attempt the following problem. I'd like you to tell me what is the hydroxide ion concentration in a 0.50 molar hydrochloric acid solution. And remember, since hydrochloric acid is a strong acid, you can think of it as a source of H plus or H3O plus in solution. So let's take about 3 minutes to work through this problem, and let's try to submit any questions or responses that we have in the chat or verbally. And if there are any questions you have as you work through these problems, I'd be happy to answer them. So how's everyone doing working through this problem? Does anyone have any questions or proposed responses that they'd like to share? You can also share what equation you're using to solve this problem and which numbers you're plugging into the equation, and I'd be happy to provide feedback.
I use 10 to the negative 14 divided by 0.5, but I don't know how to calculate.
Yeah, that's the way that you went about solving that problem. That's exactly correct. Yeah, that setup is perfect. So to provide a little bit more guidance and to flesh out and sort of show on the whiteboard what was done. So we know that Kw, which is 1 times 10 to the negative 14th molar squared, is equal to the concentration of hydroxide times the concentration of H3O plus. We know that since hydrochloric acid is a strong acid, it completely dissociates. Now, the reason why this is important is because hydrochloric acid is a strong acid that completely dissociates, we know that the concentration of hydrochloric acid is equal to the concentration of H3O plus. All of our hydrochloric acid is being used and dissociating to make H plus, and by virtue of that, H3O plus in solution. So we know then that the concentration of H3O plus is 0.5 molar. So then if Kw is 1 times 10 to the negative 14th molar squared, that's equal to the concentration of hydroxide times the concentration of H3O plus, which is 0.5 molar. We then know that the concentration of hydroxide is equal to Kw over the concentration of H3O plus, which is equal to 1 times 10 to the negative 14th molar squared over 0.5 molar. And that in turn gives us, if we punch it into our calculator, that just gives us just one moment.
2 times 10
Yep.
to the negative 14.
Yep, exactly right. That gives us 2 times 10 to the negative 14th molar. Does this example make sense to everyone now? Does that provide a little bit more clarification in how to go about solving these problems? Does this make sense to everyone so far?
Professor, how come I get 2 to the negative 13?
Because if you're dividing 1 times 10 to the negative 14th by 0.5, so if you punch this into your calculator, 1 over 0.5 just gives us 2.
So how are we supposed to calculate it again?
So in terms of the numbers that you'd input into your calculator, so you'd enter 1 EE negative 14. So that's the first set of numbers. Then you'd enter the division symbol in your calculator, then parentheses 0.5, and then you'd hit the equal sign.
Okay, so we need to enter the parentheses.
Yes, it's good practice because this is the common way that you'll enter these problems into your calculator. And you enter the parentheses just because if this number had a power of 10, you'd enter the power of 10 before closing the parentheses.
Okay, and then the negative 14, we go through the plus and the minus. So.
Yep, exactly right. So you'd enter 14 and then you'd enter the sign change symbol.
Okay, I was not entering the parentheses, so.
When you enter this into your calculator, do you get the correct result?
Should I get what? What should I be getting?
2 times 10 to the negative 14 at the end.
Okay, I'll calculate it right now.
Okay, perfect. Okay, so let's talk a little bit about how we measure acidity and basicity of solutions. So pH and pOH are measures that are designed to reflect the acidity or basicity of a solution, and pH and pOH are designed to handle the small numbers typically observed for H+ and hydroxide concentrations. So pH is defined as negative log of the concentration of H+, while pOH is defined as the negative log of the concentration of hydroxide. Now, if we wanted to solve for the concentration of H+, we know H+ is equal to 10 to the power of negative pH, while the concentration of hydroxide is 10 to the power of negative pOH. This is a property of logarithms where the anti-log is just raising 10 to the power of a number. Okay, now what's useful to note is that the pH plus the pOH is equal to 14 for water at 25 degrees Celsius. Now, remember how we said for water at 25 degrees Celsius, the concentration of H+ is 10 to the negative 7th molar? Well, the pH for water at 25 degrees Celsius, otherwise known as a neutral solution, would be the negative log of the concentration of H+, which is negative log of 10 to the negative 7, which is just 7. Now, one thing that I want to show you is just a shortcut for approximating log values. You'll need to enter this into your calculator, but this is a good way of just checking that you've done things properly. So when you take negative log of a number, let's say we call this 10 to the negative n, where n is that number. Okay, so essentially what happens when you take the log of 10 to the power of something is you're quite simply just moving this number outside of the log. So for example, negative log of 10 to the negative n is just equal to n. Okay, so your pH should roughly equal the power of 10 in most cases. This is just an approximation and it helps you avoid potentially reporting an answer that's way off in magnitude. Does this look familiar from any of your math classes where they discussed logarithms?
Yeah.
Okay, so let's try to see how this works in practice. So what is the pH when the concentration of H+ is 10 to the negative 3rd molar? So we know that pH is equal to negative log of the concentration of H+. So we're taking negative log of 10 to the negative 3rd. Okay, and if we punch that into our calculator, we get positive 3. So we have a pH of 3. In general, a quote unquote acidic solution has a pH of less than 7. Does this make sense to everyone? Is everyone comfortable with this calculation so far? Can I get some feedback in the chat that everyone's feeling pretty comfortable with this so far?
Professor, can you scroll down a little bit? I wanted to see the answer that you got on the top page really quick. Right there's fine. Thank you. Got it. Thank you.
Okay. Okay. So let's now work on this next example for about 2 to 3 minutes. So I'd like you now to calculate the pH of a 0.002 molar hydrochloric acid solution. So let's try to work on this example for about 2 to 3 minutes. And don't be shy to submit your responses or questions in the chat or verbally. And we'll discuss this example in about 2 to 3 minutes. Oh, oops. Sorry, one moment. And if you have any questions or proposed responses, don't be shy to ask your questions or share your responses verbally or in the chat.
I'm a little lost on how you got the +3.
So you enter 10 to the negative third, and then your calculator, you hit the log button. So you enter 1 EE negative 3, and then you hit the log button, and then you hit the sign change button.
Which is the log button?
It should have the letters LOG on your calculator.
Oh, I see it. Okay, thank you.
Perfect. Mm-hmm. Does anyone have a proposed response for this question? Does anyone have a proposed response for the pH of a 0.002 molar hydrochloric acid solution?
Hey, Professor, I got a TI-30X calculator, and I'm kind of confused on how to input it. I mean, I get how we get the +3, but I'm confused on how we input that on our calculator.
So first you'd enter the 1 EE negative 3. Then you'd hit the log button.
Okay.
And so your calculator should give you at the end of this first sequence -3, right?
It just keeps saying syntax error. So I got 1E, because it's just giving me the 1E log parentheses.
Did you enter 1 EE negative 3?
Let me try that real quick. And then log, you said?
Yes.
Yeah, it keeps telling me syntax error.
So you entered 1 EE negative 3, and then hit the equal sign, and it should show you a raw number.
0.001.
Yep. Now hit the log button.
Okay.
And now you should see -3.
Let's see. Not doing it. It's okay. I'll just wait until.
One moment. Let me share my camera. And you have this is a TI-30XA, correct?
Yeah, TI-30X. And then perfect. It says 2S right after it.
Okay. Okay. So let's share the rear camera. Okay. So, oops. Okay, so first thing we're gonna do, just to showcase the first calculation. So we're gonna enter 1, then EE -3. So that's what we have first in our calculator. We're gonna hit the equal sign. Is everyone following along okay from here?
Yep.
Now you just hit the log button, which is this one right here. And you should get -3 out. Does that make sense?
Yeah, I think we have a different calculator and it's telling me it's syntax error. So I think I might just have to play with it. Yeah, mine is not that one, the other calculator that.
Okay. I can certainly help during office hours. That's the general process. You enter the number and then you hit the log button. Make sure it's the log button, not anti-log or another variant of that. It should just be log.
Okay,
And it can either be a primary or a secondary function.
got it.
If we do have that calculator, what do you do after this step?
Then you just hit the sign change button to account for the negative sign, and that gives us 3 as our final answer. And the sign change button is right here.
Oh, I get it. Okay.
Does that make sense?
Yes, got it.
Perfect. So, does anyone have a proposed response for the second problem? Does anyone have a proposed response for the pH for this 0.002 molar solution? Don't be shy to share it verbally or in the chat. I'd like to see a response before we discuss. Okay, so let's talk about this. So we know that the concentration of H3O plus is going to match the concentration of hydrochloric acid, since hydrochloric acid is a strong acid. And that concentration is 0.002 molar. pH is equal to the negative log of the concentration of H3O plus. So we enter in negative log of 0.002 molar. Okay, so punching this in, we enter in 0.002 into our calculator. And then all we have to do is hit the log button right here. So we enter in log, and then we hit the sign change button. And that in turn gives us 2.698 that we in turn round to 1 sig fig of 3. This is the raw number that you should get out from your calculator, however. Does this make sense to everyone? Is everyone feeling a little more comfortable entering these values into their calculator?
No, I didn't quite get that.
So just to showcase it one more time, you enter 0.002 into your calculator, then you hit the log button, and then you hit the sign change button, which is down here.
Okay, got it.
Perfect. Okay, so online calculators can also do this as well, and that can serve as a secondary check. But if you're having trouble with your specific calculator, I'd be more than happy to work with you during office hours to help you get everything sorted out. And sometimes the calculators each have their own little intricacies in terms of how they like to process numbers. So let's now look at another example. This time where we're looking at the pH for a sodium hydroxide solution. So in this case, we know that the concentration of hydroxide is going to match the concentration of sodium hydroxide, which is our strong base, and which would be 1.00 times 10 to the negative second molar. Now, we know that we can relate the concentration of H3O plus and OH minus using Kw. So then we can solve for the concentration of H3O plus. And so we take Kw over the concentration of hydroxide. And that in turn gives us 1 times 10 to the negative 1.00 times 10 to the negative 12th molar. Our pH is equal to negative log of H3O plus. So that gives us negative log of 1.00 times 10 to the negative 12th molar, which gives us a pH of 12. So the only thing that's new in this process is that we've combined our use of Kw with our pH equation. So you use Kw to solve for the concentration of H3O plus. And then once we have the concentration of H3O plus, we simply enter it into our pH expression.
How to put the 10 to the negative 12 in the calculator?
Sure. So let's talk about that. So first, so showing how we'd enter this into our calculator, we'd start with 1 EE negative 14. Okay, so that's our K. Oh, whoops. Okay, one moment. So we enter 1 EE negative 14. Okay, then we're going to divide by this 10 to the negative second term. So we divide by 1 EE negative second, and we close our parentheses and hit the equal sign. And you should get 1 times 10 to the negative 12th. Does that make sense to everyone so far? We're right here in our process. Is everyone following along okay so far?
Yes.
Then we hit the log button, and then to finish off the problem, we hit the sign change button. And that in turn gives us a final calculated pH of 12. Does that make sense to everyone? Did that address the question in terms of how to handle this problem in your calculator?
Yes, thank you.
Perfect. Okay, so let's keep going with this and let's sort of try to place these pH values and concentrations into perspective. So for acidic, basic, and neutral solutions, so anytime you have a pH of less than 7, we are dealing with an acidic solution. So acidic solutions have concentrations of hydronium from 10 to the 0 to 10 to the negative 6 and past that. Conversely, they have very low concentrations of hydroxide.